let me introduce now our next student. Our next talk is a PhD student who is Nathaniel Hudson, a computer science PhD student working with Hannah Humphrey, who will tell us about behavioral opinion maximization in online social networks. I'd like to maximize everyone's opinion here to enjoy the following talk. Take it away, Nathaniel.
All right, thank you for the introduction, Dr. Finkel. And without further ado, I will start my talk. So the talk that what I'm going to talk about is a paper that was recently accepted for publication through IEEE Transactions on Network Science and Engineering in collaboration with my doctoral advisor, Dr. Hannah Humphrey. And the paper is entitled Behavioral Information Diffusion for Opinion Maximization in Online Social Networks. So first, we need to talk about what exactly is information diffusion in the context of social networks. And essentially, information diffusion is largely focused on how does information spread in online social network spaces or just general social network environments as a whole. And a lot of the emphasis has been placed more so on word of mouth marketing. So if someone is interested in an idea or a product, how does their communication with their peers, their family members, their friends, their colleagues, etc., how does that impact or further diffuse information throughout a social network? And so we model this in various different ways, but typically it's mathematically using a litany of different types of diffusion models. And this problem is becoming more prevalent as people become more and more reliant on the use of online social media platforms like Twitter and Facebook in order to get their political news and other forms of news and current event information, such as the COVID-19 pandemic that is going on right now. And in the literature of the information diffusion space, there is a very prevalent problem that was posed originally in 2002 by Kemp, Kleinberg, and Tarda, and it's known as the influence maximization problem. And essentially the goal of the problem is to consider a social network topology or a graph composed of nodes and edges, and you have some seeding budget K. And the goal is to essentially maximize the expected spread of information given this budget. So the idea is if you have some budget K, you are able to select K nodes in the network, and through word of mouth marketing, they're able to interact and communicate with their peers, colleagues, friends, etc., in order to spread this information to their peers. And the goal is to essentially maximize the expected return you get from the set of nodes that you initially activate to start this information spread. The problem was proved to be NP hard, and it's one of the most prominent problems in this area of study. However, that being said, there are a few issues with the influence maximization problem, and one of the most prevalent issues that I want to highlight in this talk is what I like to call the preaching to the choir phenomenon. As some of you might know, recently Apple released their latest iteration of their iPhone product. And so obviously Apple wants to make sure that people are purchasing their new smartphone and they're going to have some type of budget in terms of advertisement. So they want to make sure that the most amount of people purchase their smartphone, and they might go on social media platforms to advertise their new phone. So let's kind of simplify it a little bit. Let's say Apple can only advertise their new iPhone on one subreddit or a few people on one subreddit. Now, one option that will probably result in a lot of people being activated and buying the smartphone would be the Apple subreddit. But the problem with targeting the Apple subreddit is that these people are very likely to go ahead and buy this iPhone anyway. So Apple wouldn't necessarily gain as much by targeting this subreddit exclusively, because these people probably or likely already have their credit cards ready and pulled out to start their pre-order when it's available. So unless you consider initial opinion going into the diffusion process, you might make redundant choices. And with that said, That's why we are interested in studying the opinion maximization problem, but we also want to consider the initial opinions and also the behavioral dynamics of individual users in a social network topology. And for that, we propose the behavioral independent cascade model for diffusion. In this model, we consider a directed graph, and this graph has a few new elements. So as with any other social network topology, we consider a set of nodes and a set of edges. But in addition to that, we also consider a vertex or a vector of personalities, where we consider each node or each user node in the graph to have its own personality based on the 5-factor model, which is supported in social scientific literature. And the reason why we wanted to consider personality is because it's been found that that has a heavy hand at how often people engage in online social media platforms. So for instance, it's been found through Pew Research that 80% of all tweets in the United States are generated and created by only 10% of active Twitter users. So it goes without saying that a certain personality is more likely to be more engaged or even susceptible with the generation and spread of information. So we wanted to consider that factor. And additionally, we considered the opinions of nodes. And we consider opinion to be a value between 0 and 1 for every node in the social network topology. With that said, in order for information to propagate, we consider the propagation probability from an activated node U to an inactivated node V. So the likelihood that an activated node activates one of its neighbors to be a function of a few different gains. We consider a behavioral gain, which is essentially what is the impact or the influence that the recipient node's behavior plays into their perceptibility towards being activated by some information. And then we also consider what we call the homophilic gain. So people are more likely to, it's been found in the social scientific literature that people are more likely to be won over by those that they consider to be of the same mindset as them. So if you are listening to someone that you kind of consider to be within your own circle or opinion, you're more likely to tune into what they have to say. And additionally, we consider another term or a power that essentially represents the number of activation attempts. So we also consider that activation attempts can be numerous rather than just being in one shot, which is how the standard model known as independent cascade approaches it. So we see this, we generate the propagation probabilities essentially as a function of behavior and also opinion similarity. And now I'm going to provide like a high level explanation for how we update opinion under our model. So if a node is activated or has been activated in the past, their opinion is assumed to be 1, the maximum value. So essentially they've been polarized to 1. However, if a node is unactivated, but one of their in-neighbors or nodes that can influence their opinion is activated, then they can undergo one of 2 different types of opinion updates. The first is known as a generalized update, and the second of which is a penalized update. As I mentioned earlier, there can be multiple different rounds of activation attempts that an activated node can undergo. However, on the first activation attempt, there's going to be a little bit more penalty associated with that, because it's been found in the social scientific literature that when people are exposed to information that might run counter to their own beliefs, they're more likely to double down on their own predisposed beliefs. So we wanted to kind of include that consideration here. So in the penalized update, what happens is if an activated node fails to activate an unactivated node, then the penalized update is going to make sure that that node listens to more of its negatively opinionated nodes that it affiliates with. Whereas in the generalized update, it's a little bit more friendly in terms of the opinions that it considers when it updates its opinion. And these updates essentially follow a weighted averaging model. However, if there's a node that doesn't have, if there's an unactivated node that doesn't have an activated in neighbor, then the opinion is unchanged. With all of this said, we then consider the opinion maximization problem, which is defined as follows. If we consider a social network topology, as mentioned earlier, a budget K, and a time horizon, the goal of the opinion maximization problem is to choose a set of nodes, S, such that the expected total opinion at the end of the diffusion process has been maximized. And the only constraint on this objective is that the number of nodes in the seed set has to be equal to our budget. Some of the properties that we were able to prove regarding this problem under our behavioral independent cascade model is that the problem is NP hard. However, the objective is not submodular. And that's important because it's because the independent cascade or the influence maximization problem does actually exhibit submodularity. And this is an important note that I will return to when I show some of my results, but just make a mental note of that for now. Then we adapt a state-of-the-art influence maximization algorithm so that it considers some of the nuances of the opinion maximization problem. So we adapt the fast length algorithm, and essentially this algorithm can be decomposed into 3 different parts. The pseudocode is provided on the right. You don't need to read through that extensively, but more or less there are 3 chunks to consider. In the first chunk, the first part is going to initialize some influence and penalty matrices. These matrices will be used to essentially gauge the amount of influence and penalty associated with activating any given node. So we want to provide some type of estimate for each node going into the actual seeding process. So once those are initialized, the second block, which is highlighted in blue, approximates the influence for all of these nodes. So it actually populates the influence matrix. And then the final block, which is highlighted in green, essentially undergoes the seeding process. So it'll select K nodes in a greedy fashion, but then upon each choice, it'll also adjust the influence and the penalty matrices in accordance to that. And when this algorithm is run, it is given the social network topology, the seed budget, and also an iteration threshold, which we set just to be equal to 2. And then the output is the set of seed nodes that we want to use in order to solve the opinion maximization problem. And now I'm going to kind of show some of our initial results, which I think are pretty interesting. And first, when we were going into these experiments, we had 3 central questions that we were interested in. First, we wanted to see how the total opinion achieved by our adapted algorithm and the baselines that we look into, how does that compare? How do those compare? Does our algorithm do better? Does one of the baselines do better? That was the most immediate question. But following that, we also wanted to see how, if there's a discrepancy between the number of activated nodes and the total opinion achieved by these algorithms. And then finally, we wanted to look into the impact of community and the initial opinion distribution in the social network topologies. And for this work, we consider 5 different real-world online social network topologies that were provided by the SNAP lab out at Stanford. And the reason why we selected these 5 graphs or social network topologies is that they come with ground truth community structures, which essentially let you know the tightly associated groups of each of these networks. So we ran some experiments across all 5 of these, but I'm only going to show some of the more interesting ones just to kind of focus the discussion a bit. Our baseline algorithms that we compare are adapted algorithm 2, or the fast lane algorithm, recent state-of-the-art algorithm known as TIM+, and then two simple heuristics, the first of which is just min opinion. It selects the k nodes with the lowest opinion in the network, and then out degree, which is essentially selecting the k nodes with the most nodes that it can influence. And finally, before I show some results, I want to highlight and explain a little bit as to what I mean by exploring how community impacts the results of these algorithms. We consider two different cases. We consider a community agnostic case, and on the left, you can see an example of this. If the green nodes, you can think of the green nodes as being highly opinionated nodes or nodes with really positive opinion towards a topic, and the more maroon, pink nodes being nodes that have a very negative opinion towards a topic. And you can see that the distribution of them seems to just kind of be, it doesn't make up some structure. Whereas in the community aware case, the opinion is much more tightly bound to the community and the clusters of nodes. And we assign these using those ground truth community structures that are provided with the real world social networks. And now for the community agnostic case, we see a pretty interesting result. And this is with the Facebook topology. We see that when we compare the opinion, the total opinion achieved by these algorithms to the number of activated nodes, there is a discrepancy. So in both of these plots, the x-axis is our seeding budget, and the y-axis is essentially like a normalized value to kind of give you a sense of, for total opinion, it's the total opinion over the number of nodes. And then on the right plot, it's the number of activated nodes over the total number of nodes in the network. So it's just a more normalized value. But what we do see is that our proposed algorithm is able to achieve greater amounts of total opinion in the online social network. However, in terms of activating the most nodes, it's actually bested by the FastLane algorithm. So this is true for the community agnostic case, and it's also true in the community aware case. And in fact, we see that this is even more extreme in this scenario, where the gap between our proposed algorithm and the FastLane algorithm in terms of maximizing total opinion is wider than it was in the prior slide when the community wasn't considered when initializing initial opinion of each node. So this is all very interesting, and it kind of lends credence to the fact that the influence maximization problem may not be sufficient given the realities that people hold or have their own opinions going into any diffusion process, and you need to keep that in mind. So you might be activating more nodes, but at the end of the day, you might not be getting the most bang for your buck, essentially. But we also wanted to consider one other case, and essentially we wanted to look into how does polarized opinion impact these results. And in this case, what we essentially do is instead of sampling the initial opinions for each node or for each community from a uniform distribution, we sample them from a U-shaped arc-sign distribution. So nodes are going to more commonly hold very negative opinion or very positive opinion. And this is where the non-submodularity of the problem really shows its head. So what we see is the results in terms of total opinion are very inconsistent. There will be cases where the proposed algorithm does better. There are cases where the simple degree heuristic does better. And then there are cases where FastLane does better, but there's no key trend that can really be assessed from these results. And this is from the community agnostic case. But what we find is when we consider more polarized communities, so in the community aware case, we find this is even more extreme. And what I think is interesting in these plots is that we see with the minimum opinion heuristic, in terms of activating nodes in the right plot, it's actually doing terribly. It's doing the worst across all of our seeding budgets. But in terms of maximizing opinion, it actually doesn't do all that bad. For instance, for both when the seeding budget is 40 and 50, it actually does the best. And what that shows is that when it kind of highlights this idea that even if you try to target polarized communities, you might actually just be encouraging people to double down on their opinions. And this highlights that the results of our proposed algorithm, the FastLane algorithm, et cetera, even though they activated more nodes, they actually just kind of frustrated the nodes that they reached and interacted with, and they just doubled down on their negative opinion instead. And so that's what we found pretty interesting about these results. And that gives us a few open problems for future adaptations of this work. And so in closing, we find that for problems regarding influence and spreading processes in social networks, it may not be enough to just study the influence maximization problem, and that opinion needs to be considered because it does kind of alter the outcomes of your algorithms. Additionally, activating more nodes may not always be preferable, as we saw with those later results when the non-simodular property of the problem really makes itself known. And the existence of polarized opinions remains a problem and a challenge, and perhaps a more adaptive approach where you're not spending your entire seeding budget in one shot before diffusion begins, but instead you're spending a portion of it, letting some of the diffusion take place, and then spending more of it, and you approach diffusion in a more staggered approach. That might be more tenable, and it's an open problem moving forward. And with that said, these are a few of my references, and are there any questions?
Well, let me ask a question first. All of these various heuristics you looked at, you simulated with respect to your model, is that correct?
Yes.
Right. And so it really, in some sense, comes down to a question about how good is your model? Because if your model is a pretty accurate way of thinking about how people respond to stimuli on social networks, then your results have a lot of validity. If your model has nothing to do with the way people actually work, your model has your results have no validity. So what makes you believe that your model is something like how people actually work?
That's a good question. Going into this work, we spent a lot of time going through a lot of the social scientific literature. So for instance, I mentioned the 5-factor model, and there have been a lot of analyses conducted that adopt that model to understand how people interact with information. So we tried to stay true to the observations from the social scientific literature. And so we put a lot of work on that front. However, there does remain the problem of kind of validating beyond a shadow of a doubt if this model more closely fits the trends in these types of spaces. But that problem also remains for the influence maximization problem in and of itself. And that's because those type of data, such as what tweets people like on Twitter, what people follow on Facebook, et cetera, they're very sensitive, and those companies aren't very beleaguered to sharing that openly with researchers. So that does remain a challenge. And I would love to kind of study that more in depth. But for the context of this work, we kind of base this just predominantly on what social scientists were observing in their literature and just trying to adapt some of those observations into the model more explicitly than a plain probabilistic model could perhaps capture.
Thank you. I'm sure other people have questions. I don't want to occupy all of the question period. So anyone else? Well, let me ask another question then. About how long did it take to do one of those simulations with, say, when you had 50, when the budget was 50, and you've got a network of several thousand or tens of thousands of nodes? How long does the simulation take?
It took about a week. It took a while. What's interesting, though, I didn't talk about this like at all during the presentation, but the submodularity property of the influence maximization problem is interesting because it means that a greedy solution is an approximation algorithm, but the challenge of that is that approximating the influence of any seed set takes a while. So there have been works where it might take a month to run one experiment on a large network. So it's a very inefficient algorithm despite it being a greedy and a very simple to implement algorithm. So we kind of avoided it for the sake of this work, but yeah, this was definitely a challenging part of the process, and that was pretty cumbersome.
Well, I'll have a follow-up, but Dr. Goldsmith has a question first.
So my question is very simple to ask. What next?
So like I mentioned in like one of the last slides, I think what's interesting about this work is the fact that the objective is not submodular, and we saw that to an extreme degree with the polarized scenarios. And I think many people across the world are very interested in polarization in online social network spaces. So I think kind of focusing on that and how can we combat polarization in these spaces such that we don't have that scenario where you're activating more nodes, but you're actually harming total opinion. And perhaps taking a more adaptive solution where you're activating nodes or incentivizing nodes to engage in information diffusion over a staggered process rather than in one burst at the beginning. That is something that I think is interesting and is the most obvious next step for this work.
Cool, thank you.
Let me ask you to define submodular. It's not a term that I know, and clearly it's an important term for this work.
Yeah, so essentially what submodularity is if you have a set function, the return that you get on that set function essentially decreases as the set gets bigger and bigger. So if you add one element to the set, you might see a really big gain, but as you add another element, that gain might be smaller, and you add another element and it gets smaller and smaller and smaller. So essentially submodularity means that the return on investment diminishes over time.
So here the investment would be the budget, the number of seeds?
Yes.
So from having 10 seeds, you might be able to do some value, some ability. 11 seeds might be a lot better, but adding one more seed, you can only do a little bit better, perhaps.
Yeah, and the reason why submodularity is important is because with another part of the property is that it's always going to, at worst, it's not going to expand your value at all. Like you're just not going to get any better than that. But in this case, with our work, we see that it can harm your objective. So sometimes maybe spending all of your budget is harmful to the overall goal of your problem. So that's kind of why it presents a challenge in this work.
Interesting. Well, here's my follow-up question. Given that it's so expensive to run the simulation, and I expect that also means it would be very expensive to actually do any of these heuristics, then why not choose that very simple heuristic, the degree heuristic, which takes almost no computation and works not badly?
Mm-hmm. So one of the challenges with like the degree heuristic is that, let's see if I can go back to some of my results. Yeah, so in this case, so as you can see, like here, the degree heuristic doesn't do all that badly per se, but the algorithm, so this might make it a little bit clear, the algorithm itself the algorithms that we're considering, so the proposed algorithm, the Tim plus algorithm, the FastLane algorithm, they definitely take longer than say degree, but they don't take like a long time to run per se. The reason why it took about a week for us to run these in total was essentially because we had to run these for several different large scale networks, and the diffusion model might take a little bit to get the final result. So that would be true for degree as well. But the actual algorithm being run doesn't take all that long. That's not true for greedy, however, because it is kind of a different animal in that sense.
Right. And was I understanding it correctly that when you set the, I think it was capital T to 2, that means you only have 2 diffusion steps. So the initial seed does its best to convince some of its neighbors, and then they try to convince their neighbors, and then you stop. Is that right?
Well, no. So I didn't set T to 2. I set gamma to 2, which is it's a hyperparameter for our proposed algorithm.
Oh, okay.
Yeah.
Right. Well, thank you. Are there other questions? Well, good. My mother, who was a research scientist, when she gave her first paper, she reported back to her advisor, and the first thing he said is, were there any questions? And she said, yes, there were 3 questions. And the advisor said, that's marvelous. Even 1 question is a triumph. So thank you for a triumphal presentation, Nathaniel, and hope to hear from you again in the future. But for now, we will close for this week and hope to see you in future weeks at this time. And keep current, stay healthy, and enjoy the beautiful weather. Bye, everyone.